guest today is Ted Neward. Ted, how are you, sir?
Doing well. How are you doing, sir?
I'm doing great. Got a good night's sleep finally.
Good.
Let's talk F sharp.
Let's talk.
Because you're an expert on F sharp. You wrote a book.
I co-wrote a book.
Okay.
Actually, I had 3 other authors on that book.
All right, you're a co-expert.
Co-expert. That's a good way to put it. Yes, exactly.
It's particularly, you know what, we've talked about F sharp on the show before, but I saw your talk on F sharp last night, and what I liked about it was you went through the features of F sharp like most talks do, but you not only talked about how they work, but why they were important to the language. What is it that made F sharp, in some ways, more appropriate or more user-friendly for certain situations than traditional object-oriented languages?
Well, I mean, I'm going to go out on a limb, and I'm going to tell people that I think F sharp is I think it is the better language than C sharp.
Better. That's an empirical statement. Better.
Well, I don't know if it's an empirical statement. It's certainly a personal opinion.
Okay, but it's still a strong statement.
Well, I mean, there's lots of different ways by which we can measure what makes a language better. One of them will be how directly can I express a concept that I'm interested in expressing.
Okay.
And by virtue of the fact that F sharp embraces both object and functional, it means that it will be able to express all the same concepts that C sharp can do, but because it has functional syntax built in, it will be better able to express ideas that are in more of a functional paradigm. And that's what we're starting to see, is we're starting to see more and more functional ideas creep into our traditionally very rigidly held object-oriented beliefs.
Sure. So languages like C sharp, for example, are lambdas and things like
well,
that.
I mean, lambdas, link as a whole, the notion of declarations as opposed to imperative statements. These ideas, I won't say they're unique to functional languages, but they certainly gain a lot of traction from functional languages, and functional languages in many cases espoused them successfully. And so, when we start talking about wanting to do some of these kinds of things in C sharp, what we find is we have to write a lot of code to support the concept, right? In some respects, it's very similar to, if we go back 20 years, it was always possible to write object-oriented code in languages like C and Pascal. It was just not easy to do. Not as easy as C++, and then later Java and C sharp made it be.
Okay.
So that's really where I qualify better, is does the language have first-class support for concepts that I want to express? And if the answer is yes, and in this case the concepts are some functional concepts.
Let's get specific. Let's talk about some of those concepts that F sharp supports and why they make F sharp better.
Okay. Did you have any in mind, or do you want me to just go through the list?
I wrote some down right here.
Okay.
How about, a big one is immutability of objects. People talk about that a lot.
And the main reason we like immutability is for the basic reason that, A, we don't need mutable state as much as we think that we do. And anytime I can accidentally overwrite something, we saw this back in the day in C and C++ code, where I would write an if statement as if parens x equals 5 close parens. And at the time, everybody said, well, the problem here is that the language allows you to do assignment there. And that's why both Java and C sharp said that the if must be a Boolean statement, right? It must be equals equals. But in the C and C++ worlds, we got around this by saying if 5 equals x, right? Because if you accidentally left out one of those equals and said if 5 equals x, you can't assign to a constant. The compiler would throw an error.
Okay.
But all of this goes away if, in fact, we simply say that once x has been assigned, it can never be changed. It can never be reassigned. And this is probably one of the areas of functional programming that object-oriented programmers have the hardest time believing is reasonable, right? If if I go to a room full of 20 classically trained object-oriented developers to tell them you don't need mutable state, that you can in fact program with immutable variables, well, they're not really variables anymore because they don't vary.
That's the reason why we call them variables.
Immutable values. Then a lot of them will say, but wait, that may work for trivial programs, like a temperature conversion, right? Calculate Celsius into Fahrenheit or something like that. It won't work for real programs. And the fact of the matter is, there's a lot of non-trivial programs that are written in pure functional languages, just as to offer up the body of evidence, right? There's a lot of stuff written in Haskell. There's a lot of stuff written in ML and Miranda and so forth out of the academic world, and there's a lot of very useful programs that can be written in F# as well along those lines. But the principal reason that immutable state is gaining so much traction right now has everything to do with concurrency and has everything to do with parallelism. Aside from, let's put aside the argument that programming with immutable values makes your programs easier to read, and because that's an aesthetic argument, people can, we can debate that. When we start talking about concurrency, anytime I have a value that can change, I have to protect access to it to make sure that I'm not reading it while somebody else is writing it, or it's not going to change after I read it for a certain length of time because that would somehow change the calculation I'm working with, or any of those kinds of things. I have to think about that. And it's not just about this line of code where I'm working. I also have to think about all the rest of the lines of code surrounding this, and are any of these lines of code going to be accessing this program?
Many of which you did not write.
Exactly. And so, and it's not just, am I able to update and read the value successfully? It's more along the lines of, I have to think about, if I read this value, do some computations, and write it back, I have to protect this whole block of code, because if anybody else reads it on the fly, is that going to be a problem? Not just, we know it's going to be a problem and therefore it always must be protected, but is it going to be a problem? And what kind, if this value is going to lead to this value being modified, is going to lead to this value being modified, and this piece of code over here is reading that value, just the chain starts to get really, really complicated. If I just say these values can never change, period, the end, then,
problems to worry about.
well, then I can cache these values anywhere I use them, right? I can, I can go back to them or not as I see fit. I mean, it just makes a lot of things a lot easier to reason about when you're thinking about code. And when you're talking about code bases that are in some cases going to stretch into the millions of lines, anything that we can do to make it easier for us to reason about our code is a good thing. Not even thinking about, okay, now I want to turn this into parallel, or I want to take this up into, to scale up, right? All of these, I mean, even if you don't want to write this code specifically for this particular project, as we start looking at big data and some of these other things, people working with not just gigabytes, but petabytes and exabytes of data, you can't do that in a serial fashion. You're going to have to do that in a parallel fashion. You're going to have to start thinking in more of a parallel style, et cetera, et cetera, et cetera.
Okay, so parallelism becomes much more important as big data becomes much more important, which is a trend that we undeniable.
Absolutely.
And functional languages make parallelism a lot easier.
Yes, very much so. And in many respects, even just learning the functional programming concepts makes it easier for you as a developer to approach big data and be able to think about big data successfully.
Okay, all right. Let's move on to the feature.
Okay.
You mentioned recursion over iteration.
Yes.
As a feature of F#.
Yes.
What do you mean by that?
Well, it's. I wouldn't necessarily go so far as to call it a feature of F#, simply because we can recurse in C# and so forth. But when we look at functional languages as a whole, they prefer recursion from the simple perspective that most functional languages, via use of tail recursion optimization.
Wait, let's define that.
Well, okay, tail recursion optimization, normally when you're in C# code, or Java, or C++, or whatever, and you want to recurse, right, you have a method frame on the stack, and if you want to call another method, the compiler or the virtual machine creates another method frame. It pushes all of the parameters onto the stack, sets up the return address on the stack, etc. Then inside this method frame, they copy the parameters off the stack, you do your work, and then you basically pop the stack to come back to here.
Okay, most of us don't deal with that level.
But you need to understand that, because that's what makes recursion expensive.
Okay, I see.
Right? Because the cost of creating all those stack frames and then getting rid of them over time, right, as you start popping the stack frames back, all of that is what's expensive about recursion, as opposed to iteration, where it's all just happening inside the same stack frame.
Yeah, which is a for loop, basically.
Right, exactly. Now, tail recursion optimization says there are certain cases, if you set up your recursive call correctly, the compiler, particularly native code compilers, Haskell, ML, etc., they can look at that and say, you know what, we don't actually need a new stack frame because we're using the same basic parameters. We can actually engineer it so it all happens inside the stack frame.
Oh, okay.
And so one of the things you will see in some of these functional languages is the notion of like infinite sequences, right? Being able to recursively walk through an infinite sequence. Now, to an OO programmer, the idea of trying to iterate across an infinite sequence is clearly a bug, right?
Right.
We call that, we call that basically just an infinite loop.
Right.
But these functional languages, they look at sequences a little bit differently. In some cases, these sequences are lazily evaluated, right? So we don't actually have a list of an infinite number of integers. We have an enumerator that knows how to produce the next integer on demand.
Okay.
This is all part of this idea that I want to just continue to recurse inside the same function over and over and over again, because even if it is infinite, I'm not going to blow the stack, because it's all happening inside the same stack frame. Now, Taylor recursion optimization gets rid of the performance penalty that we associate with recursion. The main reason functional languages like recursion has everything to do, again, with immutable values. Because if I'm iterating, if I'm calculating Fibonacci in a for loop, I have to be constantly updating a counter or some sort of, accumulator total or any of those kinds of things. I'm constantly updating that thing as I go through, right?
Okay.
I have to know what the current value is, the previous value, the one before that, and I have to keep updating these as we go, et cetera, et cetera. So I'm constantly changing my state as I go. If I do Fibonacci in a recursive style, I can do it with all immutable values. Because essentially that interim state that we talk about, instead of being held in a destructive update variable, it's being held on the stack. And as long as the stack is not going to blow up because of recurse too far, because of this Taylor recursion optimization, then I am getting all the benefits of immutability, but I'm doing so in a completely 100% thread-safe fashion. Because by definition, these values being held on the stack are per thread.
Okay.
It's also generally a lot easier, particularly with pattern matching, which I'm assuming we'll get to later.
Right.
It's also in many cases a lot easier to write some of these functions by doing so, by defining them recursively. A lot of times, I know for myself, and a lot of times as I'm talking with other programmers, trying to think about something inside of a loop and think about all the different cases and so forth, it gets a little confusing. You've got too many cogs, too many wheels sort of moving all at the same time. If you break it down and sort of do it recursively and say, okay, I'm going to, Fibonacci, I'm going to walk through and just keep calling it recursively all the way back down to 0, and the 0th case is constant 0, and then we can start walking back and adding those values together.
Okay.
This becomes easier to realize.
For those who don't know what Fibonacci is, it's a series where each number is determined by the number before. You're adding up all the numbers up to a given number.
Right. And part of the reason Fibonacci comes up here is because that is kind of the hello world of functional languages.
It's a good example of a continuous series that could go on forever.
Exactly. We just see it all over the place in all these different functional examples.
And you also mentioned a phrase that I hear a lot, and I don't hear it defined a lot.
Okay.
Thread safe. Can you define that for me?
So, thread safe basically means, well, depends on the context, it can mean a couple different things, right? Generally speaking, when we talk about thread safety, what we're talking about is, can this code be executed across multiple threads without stuff going wrong, right? Doesn't necessarily mean the code will generate a null pointer exception, but I'll give you a perfect example of code that isn't thread safe. Imagine we have basic imperative expression x equals x plus 1, right? And you and I are two separate threads, right? And x is the value held in this, we'll call this x for the moment.
Okay.
Now at the time you read x, right, you're thread 1, you read x and it currently reads 4, okay? Now, the gods of thread switching, who are always a capricious and malicious bunch. They will always switch threads out at the worst possible moment. You have to assume that when you start reasoning about your multi-threaded code. The gods of thread switching have decided that after you read the value 4, I get to go. And so I read the value 4.
Okay.
Right? Now, the gods have decided that I get to continue. Right? Because remember, I read 4 because I want to add 1 to it and then store it back in here.
Yep.
So I add 1 to 4, which makes, of course, 5, and then I get to store it here. Now we switch back to you. Your value that you read is still 4. You add 1, 5, that stores it back here. Logically speaking, we as programmers say if 2 threads each added 1 to x, it should go x plus 1 means 4 plus 1 plus 1 is 6. That's the right value. But because we were interleaved like this, we each read x, right? We each added 1, we each stored 5 back. In the case of adding 1 to x, the fact that we missed 1, not a big deal. But if you and I are both depositing $100 into the same bank account, this becomes a problem.
Right.
And so in this particular case, we would say that this code is not thread safe, because what we really should have done is we should have protected the whole expression with a lock. Acquire the lock, x equals x plus 1, release the lock, right? So you acquire the glass, you read x, you add 1 to it, now it's 5, I acquire the glass, now it's 6, now it's the correct value. Thread safety is also sometimes used to mean that I can use this code without any concern for whether it's being used for multiple threads or not, right? So a lot of times in the libraries, like if you look inside the base class library or whatnot, when they say this method or this class is thread safe, it means you can use it from a separate thread or not, nobody cares. If it's not thread safe, then typically you, the developer, have to think about, do I need to put a lock around this, or can I get away with not? You know, just because it's not thread safe doesn't mean you can't use it without locks. It just means you have to think very carefully about this.
Okay, that's a very good explanation. Thanks. This is one that I really don't know at all.
Okay.
In fact, I don't even know how to pronounce it. It's
Okay.
either pronounced tuples
Or tuples. Yes, yes. One of the great debates of computer science is that particular question.
Who's right?
Are they tuples or tuples? I pronounce them as tuples,
Okay.
which means by definition it's tuples. Tuples is right.
Because
right?
it's
because
your
me.
opinion.
Because it's
Right.
me that said that. Yes, yes.
Just so you know, people that disagree with Ted are not evil.
They're just wrong. Exactly. So a tuple essentially is an unnamed bundle of data. Okay. So the basic concept is this. There are times when we're working with more than one value, right? And we want to sort of pass them around as a collection. Now, in some respects, we could go ahead and say, okay, I've got a, let's say a collection of strings, right? First names, right? Ted, David, Frank, Homer, etc. Those are all collections of first names. But occasionally we want to work with a collection of data that's not all of the same type. And the collection classes in .NET don't deal with this particularly well. Of course I can create a list of object, right? And then I can have a string and an int. But all I really want to do is I want to represent just a bundle of data.
Okay.
Historically, what we've had to do is we've had to create a class
Okay.
and name these fields and put getters and setters and properties and blah, blah, blah. Mm-hmm. But a lot of times we just want to work with bundles of data that are arranged positionally. Okay. And the thing that a lot of people don't realize is they've already been using tuples for years. They call it SQL Server.
The tables in SQL Server.
Well, not the tables per se, but the data returned out of the tables.
Okay.
So imagine I have a person table, right, that consists of a unique ID, first name string, last name string, age integer, address string, city, state, zip, etc., etc. It's got a whole bunch of information about persons. Okay. But all I want are your first name, last name, and age. Okay. So when I say select first name, comma, last name, comma, age from person where ... what I'm getting back is a 3-part tuple.
Okay.
Right? Now, in SQL, they will bring back some metadata about this tuple as well to indicate that the first string is a first name and the second string is a last name and the third is an int, right?
That is necessary to say in functional languages?
Well, in the case of a functional language, it's not a question of whether it's necessary, but there are a lot of cases where, for example, in some of the procedural languages we saw in the SQL world, right, there was this notion of having multiple return values, right, where occasionally, in a traditional language, C#, for example, I issue a query, and there is an implied difference between a null response and an empty collection response, right? Null somehow indicating perhaps that there was an error in some case, or the empty collection indicating that yes, I issued your query, but there were no results. We use null as a special signal in some cases.
Okay.
It would be better in some ways for me to say, you know what, I would like to know because we're asking basically two things. Was this statement correctly executed and were there any results? Technically those are two return values.
Right.
In a language that doesn't support tuples natively, like C#, right, I have to explicitly create a class that says query result with a field, query successful, and then collection results or something along those lines. Right. In F#, we say, look, it doesn't need to be a formal class. It doesn't need to have all of the structure and all of the domain modeling and so forth that we normally associate with classes. It really just needs to be a two-part bundle of data. Did it run successfully and what were the results, right? And this is basically what we're going to use tuples for, among other things. So in some cases what I'm going to do is I'm going to simply say, you know what, I have a very, very simple need to record first name, last name, and age. And so I'll just have a three-part tuple, which in F# is represented as string, star, int.
Okay.
And that's the type. Right? Now F# is a strongly typed language, so if I try to take an instance of this string int tuple and assign it to any other typed variable, right? So if I try to assign it to a string tuple, or if I try to assign it to a string or anything like that, it's a compile error,
right,
because it's a string int. The problem with tuples, as we kind of alluded to earlier, is that they don't have any identifiers to them. It's just a string int.
So the order is important.
The order is critical. And particularly when we talk about strongly typed languages, one of the problems is, is it first name first or is it last name first, right? Which of those two strings is which? Particularly if we talk about like vectors or something like that. If I see a vector and I see it's a float, is that an XY coordinate or is this a direction magnitude or is, what is this? And so F# also supports the notion of records. And records are basically tuples with named fields to them.
Oh, okay.
So now I can say I have a record that is string first name, string last name, int age. So that now when I say first name equals Ted, it's very obvious to me as a developer.
That's closer to what I would think of as a class, and I'm sure.
So records,
fields in it.
yeah. So if we want to look at it, we can have objects over here. Right? We have primitive types over here, and tuples are basically lightweight collections of primitive types arranged positionally.
Okay.
And records are tuples with named things to them, and classes are records that have kind of grown up and had intrinsic behavior attached to them.
Right. Okay.
Right? And that's the nice thing about F#, because in C# we have primitive types, and then we have classes. And there's really not a lot in between there.
I see, okay.
And one of my contentions is that in object-oriented languages today, in Java and in C#, and it's, quite frankly, it's more pronounced in Java, we are writing too many classes.
Okay.
There are too many places where we're writing classes where we really just need a bundle of data.
You're right, we call this data transfer.
Exactly, right, exactly. The Java world is where we started that particular pattern to say, I just want to create a DTO, a simple thing that carries a bunch of data, and in this particular case, we created them in order to carry them from my servlet over to the EJB server and back again, right? And because of the similarities between Java and .NET adopted this pattern as well. Okay. DTOs are basically just tuples, the end.
Okay, that helps a lot. Because I use that in my object-oriented program. I use these DTOs. And all right, so an F# or another function, they're easier to create. Is that that's the ability advantage here?
Yeah, a tuple is basically parens, value, comma, value, comma, value, close parens, and now you have a tuple.
And we cannot add behaviors to them, so we know what they are ahead of time.
Correct.
We can pass them to other.
A tuple is just data.
Okay.
A record we can add methods to, but quite frankly, that's kind of a code smell in some respects. Okay. If you're adding a lot of behaviors to your record, it really just wants to be a full-fledged class.
Okay. The end. All right, well, let's cut to the chase here. What is the most important feature of F#?
Well, I mean, you heard me say it last night. I think the most important feature in F#, personally, is pattern matching.
And why is that? And first of all, what is that?
So, pattern matching, in some respects, the best way to describe it to a C# or VB developer is to basically say pattern matching is switchcase, but on steroids. Good steroids, not bad steroids, right? These will not like make you get all angry and and throw your laptop out the window or anything. So essentially, pattern matching is it's kind of like all of the other decision-making capabilities in the language kind of grew up and merged in some respects. A pattern match, like most other things in a functional language, pattern match is an expression, right? If then else in F# is also an expression. So I can say let result equals if day is odd, true, else false, right? It's very much like the conditional operator in C#, the question mark colon operator, right? Mm-hmm. That always returns a value. If then else in F# returns a value. Okay. Pattern matching also returns a value, right? So everything, for the most part, everything in F# yields a value. They're all expressions, not statements. And so we can use pattern matching in much the same way as we do in if then else, but it has a lot more power, and it's more than just, it's basically if, else if, else if, else if, else if, else if, else. That's why I say it's like a switch case. Right. But one of the things we can do with pattern matching is we can also do what the functional guys refer to as data decomposition. So imagine for a moment, I'm going to have a list of persons, right? And persons, again, are classes with first name, last name, and age. And what I want to do is I want to go through this list and I want to find everybody who's older than a certain age. Okay? Everybody who's older than 40, right? And
those are the guys who rock.
Exactly. Now, in a traditional OO environment, like we see, again, I'll pick on Java here, because C# has links, so some people are actually doing more of the functional thing with, linked objects and whatnot. In traditional Java, the way to do this would have been, I'm going to create an iterator over the collection, and while I'm in this iterator, I'm going to say, if age is greater than such and such, then do this. Okay. The problem with that particular kind of coding style is that it's not particularly reusable, and that it becomes if the test that we're doing that's filtering out these persons, if it's not just people older than 50, now it's got to be people older than, or older than 40. If it's not, it's got to be people older than 40 who are also on Medicare, who are also taking Viagra, right? These are the kinds of queries and so forth that marketing guys want to do.
All right, don't say what you say.
I'm not. I'm looking at the thing here, right? And that code starts to get a little convoluted, particularly when we start saying, well, what if he's 40 and not on Medicare and taking Viagra? What if, et cetera, et cetera. So a pattern match basically allows us, if I were going to write this code in F#, I'm going to walk through, I'm going to basically recurse over this list. Mm-hmm. So I'm going to have this method called, find old guys on Viagra. And it's going to take the list. And again, the return of this is going to be a list of the stuff I'm looking for. Okay. And in the body of this thing, I'm basically going to say match, and I'm going to have a series of cases separated by a vertical pipe symbol. And I can say, okay, first of all, if it's the empty list, well then there's nothing in the list, return an empty list. Right? We start with the most common case first. Okay. Because like a switch case, we're going to go through each clause top down until we find one that works. Right? So we want to make sure that specific cases are towards the top, and the more general case, with the most general being the default catch-all, which is indicated by underscore. Okay. That's just pure functional history there. Okay. So, vertical pipe underscore means default. Okay. And I can say, all right, if this list has an element at the head, and if it's of type person, then extract that value and bind it to a local value called P. And I can do all of that by saying vertical pipe person, or P:person, rest of the list. The : operator in F# is how we put lists together. So in this particular case, they're using it to say, I want to strip the head of the list off and bind it to a local value, and put the rest of the list in the other part, the tail of it. Okay. And then that tail, by the way, is what we'll call when we recurse back into this thing.
Okay, so we never call the same, we never iterate over the same entity twice.
Right, exactly. And the value here is that pattern matching not only lets me examine the value, right? Switch case lets me look at a string and determine whether or not this string matches some constant value. Switch case allows me to not only look at the value, right? So I can do a switch case using just constants, right? Match, quote, Ted, pipe, Ted. Okay. Kind of stupid, but we can do that. But it also lets me match this based on types. So imagine a switch case that allows you to do an implicit ISA along the way,
Okay.
right? Plus, it will go ahead and extract that value and bind it into a local variable,
Okay.
right? So again, one of the things I can do, we go back to tuples for a second. I want to find all of the people in this list of tuples whose last name is Neward. I can say match T, vertical pipe, parens, underscore, comma, Neward, underscore, or comma, underscore. In other words, I don't care what the first part of the tuple is, I don't care what the last part of the tuple is, I only care if the middle part matches the string Neward,
Okay.
right? Then on top of that, we can add where clauses, basically when clauses to the end of it. So I can say match person P when P dot age is greater than 40,
Okay.
right?
So everybody in your family is greater than 40 would be returned and stored.
It would match that particular clause, right? And then we would basically say, oh, okay, I want to recursively invoke this function again, and by the way, take that result and tack it on with this result that met the criteria on the front. And again, that's when we recurse, when we're sort of doing this recursive decomposition, we're taking the elements of the list, and we're basically breaking it down one by one until we reach the empty list, and then we start coming back.
What do you mean coming back? Why?
Well, again, we're recursing, right? So it's a list of 5 items,
Okay.
right? So we take the first one off and pass the other 4 recursively.
Okay.
We take the first one off and pass the other 3 recursively. We take the first one off and pass the other 2 recursively. Take the first one off, pass the other one recursively. Oh, it's the empty list. So now we start coming back and stitching the results on the lists that are coming back until we have the full results.
I see. Okay.
And at no point did any mutable state ever happen as a part of this, because it was all being stored on the stack.
And so I guess one of the big advantages of this is that would be a lot of code to write an object-oriented language. You'd have to declare those other lists. You'd have to use
Particularly
your
if you
switch
wanted-
statement. You have
yeah.
to store them, figure out the conditions inside of your switch statement, which if it was a simple match this equals that, that's
Right.
fine. But if it's
Right.
something like a is a, that'd be a lot more complex.
And then you have to
Maybe
extract it
use
into the
else
local
if it was-
variable, and then it's
And then
it's
push it
a-
into these other lists as well. And you can do it with essentially a line of code.
It's probably more like 2 or 3 lines of code in F#, but yes, I mean, this is what I mean about being
But that's
a little bit more expressive and a little bit more compact in terms.
Okay. TedNeward, thank you so much.
You're very welcome, sir. Take care.
Clean shirt, new shoes, and I don't know where I'm going to. Silk suit, black tie, I don't need a reason why. They come running just as fast as they can. 'Cause every girl crazy about a shirt that's me.
Confucius say, if technology making you friends, you don't have good friends, and you don't have good technology.